Good afternoon, everyone. Earlier this summer, Suresh and I were at the Midwest Community Day, and we were delivering a generative AI on AWS keynote. Right after the session, we walked over to a Starbucks, and on the way, we were discussing the endless possibilities that generative AI can bring on. So at the Star coffee shop, we ran into someone in the table next to us. He had an extra chair. So I walked over to him to ask if I could borrow the chair for our table. He started communicating back with me in a sign language. That is when I realized that he was deaf and hard of hearing. I didn't understand what he was trying to communicate, and I did not know how to sign back either. It was a moment of realization of a communication breakdown. Assistive technologies exist that can translate English to other spoken languages, but this was a unique problem to solve for that does not have a solution today. That's when we thought, what if we can utilize AWS Cloud and generative AI capabilities to build an application to enable individuals who rely on visual communication. With that, we are here now, very excited to show you all how we built that solution. My name is Alak Ishwaradas. I'm a Senior Solutions Architect here at AWS.
Hello, everybody. I'm Suresh Pupandi. I'm a Senior Solutions Architect with AWS.
Hey, everyone. I'm Rob Koch. I'm a Principal Data Engineering in Slalom. I'm deaf, obviously, so I'm signing, and I have a sign language interpreter in the front row voicing for me.
All right. So in this session, we're going to be talking about how to build a generative AI-powered American Sign Language avatars. So in agenda today, I'm going to be walking over what is accessibility in assistive technology. We'll talk about American Sign Language and introduce the solution we built. I will then be handing it over to Suresh to do a demo that we have teed up, and he will be diving deep into the architecture and code. This is a level 300 advanced session focused on the builder's audience. With that, let's get started. So Rob is going to get us started. Over to you, Rob.
So you see this picture here, and as we say, it's worth 1,000 words, right? So there's people here, families. There's a dad with a stroller that you can see. There's maybe a mother with a kid on a scooter here. And then, they're all walking across the street. You notice that this curb that's cut here, that with the dip in it, that's for accessibility with ease. The little girl with the scooter can get up the ramp without stopping to pick it up, let's say, and go onto the sidewalk. The stroller doesn't have to be finagled up the curb as well, and the family doesn't have to pick up their kid and put them onto the sidewalk. Maybe also an elderly person who has difficulty with making steps. So all of this is utilizing the curb, and it is called the curb cut effect. It is designed for folks with wheelchair using and accessibility to providing accommodations for folks to be able to use that who are wheelchair users. But that phrase that we take from it is called the curb cut effect, and that's where it comes from. The example of that effect is also for subtitles on the TV. That was intended for the deaf and hard of hearing, but a lot of people use them, like if you're in a noisy environment, or if you have an audio processing disorder, or maybe English was your second language, and you want to see what they're saying a little bit more clearly, it can aid in that. So the curb cut effect, that is illustrated here. I'm going to turn it back to Alec, and she will discuss a little bit more about ASL.
Awesome. Thank you, Rob. So with that, let's talk about what is accessibility. So accessibility means anyone who's using a product or a service must receive the same benefit, regardless of the condition or the disability that they may have. So it's really about identifying the barriers in the environment and really working to remove them. Some barriers can be removed by introducing special equipments that the people with disability can use, while other barriers can be removed by completely changing the environment itself, like the curb cut example that Rock talked about. So what is assistive technology? It's a set of tools that people with disability can use to accomplish the task. Visual, auditory, physical, speech, cognitive, and neurological disabilities must be considered when implementing accessibility measures. Why do we care about accessibility? First and foremost, it's the most human thing to do, right, to care about others, because if we exclude people, we're creating barriers, and therefore the products that we create become inaccessible to everyone. And then, according to World Health Organization, 15% of the population has significant disability. This includes 1 billion people. If this population were to be a country on its own, it's third next in line to India and China. Globally, more than 2.5 billion people rely on one or more assistive products. 466 million people worldwide have hearing loss, and that includes 34 million children, majority of who have hearing parents. And it's also estimated that by 2050, more than 3.5 billion people will need one assistive product. 900 million individuals will experience hearing loss or communication issues. All right, so in order for us to know the type of audience that we're talking to, I'd like to take a moment to hear from you all. So if you could please go ahead and scan the QR code, and that'll take you to a polling page. And I'm going to be reading out the question. You will have about 45 seconds. Do you all know what American Sign Language is? You'll have 10 more seconds, and yeah, it looks like we have the results already coming in. Awesome, majority of you know what American Sign Language is. It's great to know that. Let's go back to the slides. Awesome. So sign languages are visual, gesture-based language, which is regarded as the deaf or the hard of hearing community's mainstream language. Hand gestures, body movements, facial expressions are all utilized in communicating in a sign language. American Sign Language is a fully and unique language, which is having its own grammar structure, morphology, and a syntax that's unique to itself. In ASL, the smallest units of the language are combined to form a sign called parameters. So it includes hand shape, palm orientation, handshake movement, and facial expressions. So there is no human concept that cannot be accurately and completely expressed in ASL. When ASL is a primary language, English is the second, third, or the fourth acquired language. ASL is used in US and parts of Canada as well. Let's take another moment to do a poll and hear from you all. Is ASL Gloss a written language? True or false? You'll have another 10 seconds. Awesome. Yes, majority of you have the right answer. ASL is not a written language. So let's go back to the slides, please. So ASL Gloss is not ASL in a written form. ASL Gloss is not a way of making ASL a written language. So then what is ASL Gloss? It is a linguistic representation of American Sign Language. What do we mean by that? So for example, an English text, hello, how are you, is going to be represented in the ASL Gloss notation as hello, how to be. You may be noticing all the capital letters and also some hyphens being used in the gloss notation. Capital notation denotes that they are labels, and it's also readily distinguishable from the English text. Hyphens are used when the gloss is formed with more than one English word. So those words are separated by a hyphen to indicate that is a single gloss. So this occurs in instances where ASL is more efficient than English, where ASL can say in one sign what it takes 2 or more English words to convey. The other thing you may notice is the word reinvent is finger-spelled. So in ASL, when a word needs to be finger-spelled, it's indicated with the prefix FS, and every finger-spelled letter will be separated by a hyphen. All right, let's talk about why ASL avatars. Deaf and the hard of hearing individuals and the hearing individuals rely on sign language interpreters to communicate between them. Although some government agencies require American Sign Language, many private organizations, events, and individuals do not have access to sign language interpreters, which are expensive and are in short supply. With the limited availability of the human interpreters and the fund, there is a gap in communication in meetings, events, and even in the daily interactions, like the coffee shop example that I talked about earlier. There are video-on-demand platforms that allow the sign language interpreters to join and attend the calls, but they are in really short supply, and finding there are not enough qualified sign language interpreters to meet the demand. Fake signers continue to be on the news. A couple years ago, a woman got arrested for fake signing in a police interview. So therefore, we are really leaning on to the need to create assistive technology with faster and accurate translation. Lastly, the rise of the foundational models and the fascinating world of generative AI that we live in is incredibly exciting. And it really opens up doors to imagine and build what was not possible before. What is generative AI? Generative AI is a type of AI that can create new content and ideas, conversations, stories, images, videos, and music, and so on. So like any other AI, generative AI is powered by machine learning models, which are pre-trained on vast corpora of data, commonly called as foundational models. So with that, I want to introduce you all the application that we built called Gen ASL. It utilizes AWS Cloud and AWS generative AI capabilities to enable individuals who rely on visual communication by translating speech or text into ASL animations or videos. So users can simply send an audio as an input, and the Gen ASL application will generate a human-like video, and also it's going to be generating an ASL avatar. So let's dive into the solution approach. So the audio file will be passed on to a speech-to-text model, which will then generate an English text, which is passed on to a text-to-text large language model, which is going to generate the ASL gloss that we talked about. The ASL gloss is then used by a machine learning model to generate a sign video. So we have some examples that Rob is going to be showing us that was generated by our application.
Hello, how are you? I'm fine, thanks. How are you? Welcome to reInvent.
Awesome. So those examples that you saw were generated by our Gen ASL application. So having looked at some examples and the high-level idea, let's take a deeper look at our solution approach. So our solution includes 3 steps. The step 1 we take the input audio and convert it to an English text. And in step 2, we use the English text to generate the ASL glass. And in step 3, using the ASL glass, we generate those videos that you saw in the previous slide. I'm going to be diving deep in each of the steps in the subsequent slide, so I'll get into the details there. So in step 1, we convert the audio input to English text, and for that we use Amazon Transcribe. Amazon Transcribe is an automatic speech-to-text AI service that uses deep learning for speech recognition. This is a fully managed service, and it's continuously trained service. It enables you to focus on your business and allows AWS to do the heavy lifting in terms of building and maintaining the state-of-the-art speech recognition models for you. The other thing to note is that it's an AI service, and no prior machine learning experience is required to use the service. So in step 2, we're going to be generating the ASL glass. And we are using Amazon Bedrock, and specifically Claude V2 LLM provided by Anthropic. So Amazon Bedrock is going to be the easiest way to build and scale generative AI applications with foundational models. The biggest value proposition of Bedrock in the market is the ability to accelerate the development. The other reason why Bedrock shines is that it has the ability to access different foundational models, both provided by the third-party providers and Amazon-provided models as well. So Bedrock customers can choose from some of the most cutting-edge foundational models available today. So it includes Amazon's Titan, AI21 Labs Jurassic 2, Anthropic Claude V2, Cohere, Meta, and Stability AI provided models. So late September, Amazon and Anthropic came up with a partnership to advance the generative AI capabilities. And we are leveraging Claude V2 for a generative Gen ASL application as well. So with that, this third step includes generating the ASL video from the ASL glass. So our input data set, the video data set, is stored in an S3 bucket. And then we are going to be leveraging MMPose, which is an open source toolbox, and RTMPose, which is a model, pose estimation model, that's going to be generating those ASL avatar videos. Suresh is going to dive deeper when he's walking through the architecture. But really, we are going to be able to have the ASL glass as a key in the DynamoDB table, and the pointer to those videos that's going to come from the S3 location. So the video data set is from American Sign Language Lexicon video data set. It's coming from the Boston University. There are around 3,300 ASL signs, and they are produced by around 6 native ASL signers. So the video files includes multiple signs, and the metadata is important here because for every ASL class, it's going to include the start and the end frames. So having looked at the input data set, I'd like to touch a little bit upon the MMPose and the RTMPose, which is the real-time multi-person pose estimation model that's powering a solution. So you can sort of see the 2D human whole body pose estimation. So we're using 133 key points. RTMPose is able to generate those avatars. So lastly, with the input data set, we're able to generate the ASL avatars and using an MMPose pose estimation model, and we have all the data ready in DynamoDB and S3. So having talked about the high-level solution approach, I'm going to hand it over to Suresh, who's going to be showing you a demo and take us through the architecture.
Okay. Yeah, we have built the Gen ASL application and hosted that on aslavatars.com. Let's wait for the demo to show up. Okay. So let me open the browser and then go type asl-avatars.com. It's going to bring up the application we built. This application accepts 3 types of input. You can upload an audio file, and then also you can press the mic button and then use the device mic and then provide input. Also, you can type a text and then press generate video. So for the first use case, I'm uploading an audio file. It has generated the avatar video and then the sign video. So here, I pre-recorded an audio file saying that what is reInvent. AWS reInvent is a learning conference hosted by AWS for global cloud computing community. So whenever the GenASL application finds a sign in the sign database, it's going to take the corresponding sign video and then bring it back. If the sign is not available, it's going to fall back to finger spelling. So here it's finger spelling some of the words like, like a reInvent is, for example, it's going to finger spell. And then it found some sign for cloud and community. That's going to come up soon. So yeah, that's cloud, and then it's finger spelling the next one, and then the last one will be the community. So now let's move on to the next type of input. For the next type of input, I'm going to press the mic and then talk to the mic, saying that I'll repeat what is generative AI. Generative AI is a type of AI that can create net new content, including conversations, stories, music, videos, and images. So I'll stop the mic, and then in this use case, I'm using the browser's speech API to convert the speech into text, and then the text is sent it to the backend application. So the reason I chose this one here, you can see a lot of signs will be available in the sign database, like stories, images, videos, and music. Those are common words, and then they are available in the sign database. So there may be a question, why ASL avatar? Like, why can't we just stitch together video and then have a real human-like video generated? But if you see some of the signs, the signer's dress is changing, and then there is a flip between the signs. So that's the reason we are generating the sign avatar on the left-hand side. So you can see some of the dresses getting changed. So that's for the music one. And then let's look at the final use case where I'm going to type and then press generate. Here I'm going to type, let us build generative AI-powered American Sign Language avatars. Here, there are some signs available for American Sign Language avatars, but signed by a different signer. So I did not pull that into the sign database, so it's going to finger spell that word. Okay, I think that concludes the demo. Let's look at the architecture behind this. So the architecture consists of 3 parts. Let's look at the first part where the backend batch process. This batch process is going to download the video file from Boston University website and then store that in an S3 bucket. And then also it downloads the metadata file. And then the metadata file has the start frame, end frame, the sign, the ASL gloss, and the signer. So then it processes that file and segment that video file and then create multiple video file, like one file for one sign. And then it stores that in the S3 bucket and then store the corresponding S3 key in the DynamoDB along with the gloss. And then once that first step is done, the second step is avatar generation. So it's going to take the sign video and then go frame by frame. Most of the sign will be like there will be less than 2 seconds. It's a 30 frames per second video, so there will be at most 60 frames. So it's going to take the image and then send that to the 2D pose algorithm. That's like the RTM pose is a 2D pose algorithm that's being run within MMPose toolkit. That's going to create 133 key points. Some of the key points are where the eyes are, where the nose, where the hand. So it's going to give the key points, and then those 130 key points are stored in the database, and then a blank canvas image is created, and then all the points are plotted to create the avatar video. And then that is repeated for 60 times for each frame. And then the resultant, the avatar video is stored in S3 bucket, and then the corresponding S3 key is stored in the DynamoDB along with the gloss. So let's look at the front-end application. The front-end application is built using AWS Amplify. AWS Amplify is a framework allows you to build, develop, deploy, host full stack applications, including mobile and web application quickly. So I use that to generate the authentication. So you can simply add the authentication to a front-end AWS Amplify app using Amplify CLI, Amplify add auth. That's going to generate the sign-up screen, login screen, as well as the backend Cognito identity pools. We can ask, hey, why do we need authentication and then authorization for this app? Because the use case I mentioned, when we are uploading the audio file to S3, the front end has to connect to the S3 and then upload the file. That needs a temporary identity. So that temporary identity is provided by the Cognito identity pool based on the user credentials. And then let's look at the middle part, the API layer. The API layer is fronted by Amazon API Gateway. API Gateway allows you to authenticate the API request and then monitor the API request and also throttle it. So whenever the API request gets the API to generate the sign video, it's going to invoke a step function and then return the step function execution URL back to the front-end application. So let's look at what is inside the step function. The step function has 3 steps, like outlined in the high-level solution. The first step is a transcribe audio. It has to convert the input audio file into an English text. That is done through Amazon Transcribe service. And then the second step is converting the English text to the ASL gloss. Here we are using Amazon Bedrock API to call Anthropic Claude V2, and then we will provide a prompt saying that convert this English text to ASL gloss, and then give the input text message. Also, we provide some examples. So here we are using a few short prompting to instruct the Claude V2 produce some accurate glosses. And once that is done, the third step is going to create the avatar videos and then the sign videos. Like we have the data consists of only the video for each sign. So this third Lambda function is going to stitch the videos together and then generate a temporary video and then upload that to the S3 bucket and create a pre-signed URL and send the pre-signed URL for both sign video and avatar video back to the front end, and then the front end is going to play that in a loop. So let's dive deep into the API detailed design. Okay? The API gateway supports a maximum timeout of 29 seconds. So here, if you give a longer audio file, it may take more than 30 seconds. So we want to avoid the timeout issue. Also, it's a best practice not to build an application that's synchronous. So here we build a asynchronous API. So the asynchronous API is built in a 2-step process. One is a sign API endpoint with a post. That's going to get the S3 key and then the S3 bucket name or a text. So then it's going to the API gateway. API gateway is going to delegate the step function. Step function will send a response back with the execution ARN. So then the next step is going to do a get sign. The get sign is going to send the execution ARN back to the API, and then it's going to check the status of the step function execution. If it is succeeded, it's going to return the pre-signed URL back. If it is running, it's going to send a status running back, and then the front end will wait for a couple of seconds and then call the get sign again. Okay? So this is an end-to-end architecture. Here I just want to highlight a couple of things. One, when we started working on this project, we were using Amazon's vector-to-vector machine learning model with the corpus of text to ASL gloss, and then we trained that Amazon vector-to-vector machine learning model to generate that gloss, but the accuracy was very low. And then when Amazon Bedrock was introduced, we switched the algorithm to, we switched our implementation to use Amazon Bedrock's and the Claude V2 model, Anthropic Claude V2 model, then we were getting accurate results with some few examples. And then the second thing, recently on Monday, there was an announcement. The STEM function has integrations with Bedrock. So we don't need to have the Lambda in the middle. The create ASL gloss Lambda is not needed anymore. You can just call the Bedrock API directly from step function. That will save the Lambda compute costs because the Lambda is not needed anymore. And from a DevOps perspective, the front end is using Amplify to build and deploy, and then the back end is using a SAM, serverless application model, to build and package and deploy that applications. Let's see what all the other things we can add from a DevOps perspective. So any good application, we want to have a monitoring and logging. So the logging is done to Amazon CloudWatch logs, so that has been taken care. So I put together a dashboard to capture the metrics. So on the top left-hand side is displaying the number of API invocations. That's going to show how many ASL avatar videos were generated. And then the other three, average response time, is going to show how much time it took to create that video. Averaging is like around 10 seconds. And then there are two major Lambda functions inside. One is the text-to-gloss. That's taking less than a second on average because it's calling the Anthropic Claude V2 model to generate the gloss. And then the third one is the gloss-to-post. That involves downloading the file from S3 and then video processing. So that's taking close to 8 seconds. So that's average is around 10 seconds total. And then the bottom part is showing the error metrics. Like it's good to provide a good user experience by tracking if there is a failure and then alert the DevOps team. So it's capturing all the errors produced by this GenASL application. Now let's see when this application is deployed, how it's going to look like in the AWS console. So I'm logged into the AWS console, and then I went to state machine UI, and then this is the step function deployed as part of this project. And then let me open the step function, and then I'll go and edit this step function. That's going to bring up the step function in a workflow studio. The workflow studio is an easy way to drag and drop the states to create a workflow. So it always starts with start and then ends with stop function. Here the first step is an input check. The input check is checking whether the input is an audio file or input is a text. So if it's an audio file, it's going to start the start transcription job, and then the start transcription job, it's integrated with the AWS SDK. Here is an example where we don't need a Lambda function to invoke start transcription because it has a direct integration with transcript service. So here we just need to pass the URI, and then to support other languages, I left the identify language as true. And then once this step is done, it's going to return the transcription job name as an output, and then it goes to the wait state. Wait state is going to wait for 2 seconds, and then call that get transcription job status. And then it will pass the job name as an input to that one. And then once the get transcription job returns, the next step is going to check whether the job is completed or not. It's a choice state. If you look at the choice state here, there are three if-then conditions. Like one is going to check whether if it's completed, it will go to the next step to process transcription. If it is failed, it goes to the error state and then exit. And then if it is still running, it goes back into the wait, and then wait for 2 seconds, and then call the get transcription job status again. And then once it's succeeded, it's going to go to the process translation utility Lambda function. What this Lambda function is doing, it's taking the transcription job name and then call get transcription job status, and then get the text out of that, out of the job, and then put that in a variable that will be used in the next two steps. So the next step is a text to gloss. This is where it's calling the Amazon Bedrock API, and then it's going to call that Anthropic Claude V2 behind the scene by passing the English text, and then it's going to get the output gloss as an output. And then once the gloss is received, then the final Lambda, it's going to the gloss to post, is going to download the videos, stitch the videos, and then upload the resultant videos into an S3 bucket, create a pre-signed URL, and then return the pre-signed URL in the output. Now let's close this one and look at one of the job execution here. So the first one, we'll look at the first one because it will went through all the states. So let's look at the executions created for audio file upload use case. In this case, it went through all the states. It's checking the input, and the input is audio. Then it's going to call the transcription job. Here you can see what is coming in as an input, because it's going to get the bucket name and then the key name where the audio file is uploaded. And then once that is done, it's going to call the transcription job, and then it's going to go and wait. And then once its wait's done, it's going to call the get transcription job status, and then it's going to return the response back. Says if you see it's in progress, because this particular job took more than 2 seconds. So the first call returned in progress, and then the second call will become complete. And then once it's complete, it's going to go to the process translation job. Here it's output. If you see the output will be the whatever I uploaded in the audio file, what is reinvent, and that answer. Once that is coming, it's going to call the Bedrock API. The Bedrock API is getting that what is reinvent in the English text as an input, and then the output from that will be the gloss. So you can see the gloss will be like IX3Ps, he, see, what is reinvent. And then this is the next one is the gloss to pose, and then gloss to pose is getting gloss as an input, and then the output will be the present URL. You can see the URL with the large, because identity is embedded in this URL, so the URL will be present URLs are large. And that concludes our console walkthrough. Let's move on. So what is next? As you can see, the GenASL application is currently generating a 2D avatar. So we are planning to convert that to a 3D avatar. So there are 3D pose estimation algorithms already available and supported by MMPose. We are going to use that to create 3D key points. So on the 2D key points, like we saw, there are 133 key points. But when we use 3D, it's going to generate thousands of key points. So we have to store thousands of key points. So it needs a lot of compute. And then the next step, we are going to use a stable diffusion image generation capabilities to create human-like avatars, and then use the 3D key points and then the human-like avatars, and then create a realistic avatars that can be used in real-world settings. And then finally, when you see some of those videos generated by this GenASL application, there is a frame skipping. For example, hello will be like this, and then how you may start from here, from the chest, and then the hello will be on the forehead. So when we stitch the video together, there is a frame drop, like you can see a sudden change in the motion. So to fix that, we have to use a technique called blending. There are partner solutions available that will create the intermediate frame to create the blending. So our next step will be incorporating partner solutions to create smoother videos. And then also, like this is a one-way, right? We are going from audio to ASL video. We also need a solution from ASL video back to English audio. So that also can be done by navigating in the back way. So for example, like the audio is getting converted to a text using transcribe, and then from the text to gloss using Anthropic V2, and then from the gloss to avatar video is through pose estimation algorithms. So if we can do the same thing in the reverse, we can record a real-time sign video, and then take the video frame by frame, and then send that through pose estimation algorithms, and collect the key points, and then compare the key points and search against the key points database, and get the gloss, and then from the gloss we can go to text, and from the text to audio using Amazon Poly. So that's the next. So given the high-level overview and the demo of GenASL application, here are some of the important resources. You can use it to make your products more accessible. The first link is the GenASL applications hosted on asalavatars.com. You can use it to create ASL videos. And then the second one, Amazon Bedrock, allows you to create generative AI applications quickly by invoking generative AI models via API. To learn more about Amazon Bedrock, you can follow the second link. Third, Amazon's vision is to become its most customer-centric company. That means building products accessible to everyone. So you can learn more about Amazon's initiatives around accessibility and inclusivity by following the third link. Okay. If you like our session, please provide a 5-star rating. That will allow us to continue working on this project. Also, please provide feedback in the session form. That will also allow us to continue our journey as speakers. And then we are passionate about accessibility and building assistive technologies. Whenever you build a product, include accessibility measure into that. Make sure whenever you build a product for your customer and your company, make sure to think about accessibility features. And then together, let's make our world more inclusive and accessibility to everyone. Thank you all for coming to our session.